Following a launch on December 25 atop an Arianespace Ariane 5 rocket, the joint NASA/ESA/CSA James Webb Space Telescope is currently traveling toward the Sun-Earth Lagrange Point 2, L2, where it is expected to orbit and perform future science observations. Liftoff occurred at 12:20 Universal Time Coordinated from the ELA-3 launch complex at the Guiana Space Centre in Kourou, French Guiana. James Webb successfully separated from the Ariane 5 upper stage 27 minutes and 7 seconds after liftoff, beginning its journey to the Earth-Sun L2 Lagrange point after Ariane 5 successfully put the observatory on the correct trajectory to enter the Lagrange point in 30 days' time. At T+29 minutes, 8 seconds, James Webb's solar array was successfully released and fully extended. Soon after, the array went power positive and began charging up its batteries to allow James Webb to generate and operate under its own power. Due to how critical the solar array is to James Webb's operations, it was deployed automatically and not via ground commands. A few hours later, about 12.5 hours after launch, James Webb performed its first mid-course correction burn. Mid-course correction burns help keep the observatory on the correct trajectory to L2 and correct any mistakes or imperfections in the trajectory that may have resulted from the launch. The first mid-course correction burn, called MCC-1A, was the only other time-critical operation during the deployment sequence other than the solar array deployment. Success. #NASAWebb's first mid-course correction burn helped fine-tune Webb's trajectory toward its orbit around the second Lagrange point, 1 million miles, 1.5 million kilometers, from Earth. https://t.co/fcx9tom7zi number sign unfold the universe, pic.twitter.com/1fb7egbz9, NASA Webb Telescope. At NASA Webb, December 26, 2021. Of note, though Ariane 5 puts James Webb on a nominal trajectory out to the L2 point, this is not the exact trajectory James Webb will take to L2. This is planned because, if Ariane 5 had given James Webb more thrust than it had needed to get to L2, the observatory could not have then turned around and fired its thrusters to correct the burn, as its optics and structures would have been exposed to the sun's heat. If certain telescope systems, such as the optics and instruments, are exposed to the sun's heat, they will become overheated and useless, causing teams to abort the mission. At T+1 day, James Webb deployed its Gimbal Antenna Assembly, GAA, which contains the observatory's high-rate antenna that allows for communication and data transfer between the observatory and Earth. When the GAA was deployed, it was rotated to its parked position. When in its parked position, the GAA is pointed toward Earth. Additionally, the deployment of the GAA is the final automatic deployment of the 344 unfolds James Webb will be commanded to do throughout the duration of its deployment sequence. All subsequent deployments will occur via commands from the ground. After the deployment of the GAA, James Webb will perform its second mid-course correction burn, MCC-1B, at T+2 days. The exact duration of the burn will ultimately be determined by how accurately the Ariane 5 placed James Webb on its trajectory to L2. Regardless of Ariane 5 performance, this burn is expected to be short. However, from T+3 days is when the real nail-biting part of the James Webb deployment sequence begins, sunshield deployment. T+3 days is when the forward and aft unitized pallet structure, UPS, of the observatory's sunshield deploys. The UPS pallets carry and support the 5 membranes that make up the sun shield. During the deployments of the UPS, key release devices are activated, and electronics and software that support the UPS motors are configured before the deployments. What's more, the deployment of the forward UPS pallet marks the beginning of all major deployments. At T+4 days, the next stage of the sunshield deployment sequence occurs. The deployable tower assembly, DTA, will extend out from James Webb by about 2 meters. The separation between the DTA and the observatory allows for better thermal isolation and gives room for the membranes of the sunshield to deploy. As with the UPS deployments, release devices, electronics, software, and heaters have been configured to support the deployment motors. T+5 days will see the deployment of the aft momentum flap, offsetting solar pressure that affects the sunshield and minimizing the amount of fuel James Webb will have to use during its mission. Spring drives rotate the flap to its final position after being released by hold-down devices. Additionally, at T plus 5 days, the sunshield covers will release and roll up, exposing the sunshield membranes to space. The release devices that release the covers are electrically activated. At T plus 6 days, the port and starboard sunshield mid-booms deploy. This sequence includes the deployment of the 5 membranes, however, these are still compressed and have not been separated. The deployments of the sunshield mid-booms are motor-driven. T plus 7 days is when sunshield layer tensioning begins. The tensioning of the sunshield is a multi-step activity spanning 2 days that will see the final deployments and releases of the shield, and the tensioning of each of its 5 membrane layers. By T plus 8 days, sunshield tensioning will be complete, and the initial cooling of James Webb begins. Once the deployment of the sunshield is complete, the next major system to deploy on James Webb is likely the most important, the mirror and telescope optics. The first stage of the mirror deployment begins at T plus 10 days when the secondary mirror support structure, SMSS, moves the secondary mirror into its operational position. The secondary mirror is located at the end of the SMSS, and the SMSS deploys it in front of the primary mirror, where it will reflect the light from the primary mirror into James Webb's tertiary mirror and instruments. After the deployment of the SMSS and the secondary mirror, the aft deployed instrument radiator, ADIR, is released from its launch position at T plus 11 days by the last of its 4 remaining launch locks. The other 3 launch locks were released soon after launch to prevent strain against the telescope and ADIR as the observatory cools in orbit. At T plus 12 days, the primary mirror deployments will begin. The port primary mirror wing will be the first to deploy and contains 3 of the 18 individual segments that make up the primary mirror. The primary mirror wings were required to ensure that James Webb could fit inside the Ariane 5 fairing. It will be deployed in a motor-driven process. The following day, T plus 13 days, the starboard primary mirror wing deploys. Identical to the port wing, the starboard wing contains a further 3 mirrors and will also undergo a motor-driven deployment. Finally, by T plus 13 days, all major systems on James Webb will have been fully deployed, and the observatory will continue traveling to L2 for the remaining 2 weeks of its journey. During this time, the telescope will continue to cool using the sun shield and other onboard systems. Additionally, during the T plus 15 to T plus 24 day range, the mirror team will work to activate and move each of the 18 individual mirror segments and the secondary mirror that make up James Webb's mirror and optics systems. Each mirror has a small motor that allows teams to adjust its position in order to focus and calibrate the telescope. The tertiary mirror stays stationary. At T plus 29 days, James Webb will perform the third and final mid-course correction burn, MCC2, which serves as its insertion burn at L2. MCC2, when performed, will correct any residual trajectory errors found during James Webb's trek to L2, and adjust the observatory's final orbit at L2. The James Webb Space Telescope is expected to insert itself into a halo orbit at L2, completing the 30-day deployment sequence. With this concluded, instrument teams will be able to begin bringing their instruments and systems online for commissioning and use. James Webb will not immediately begin science operations once it reaches L2. It will first need to continue to cool down to reach a temperature of nearly 6 Kelvin, while instrument teams will be performing tests and calibrations on their instruments for an additional 5 months. If all goes according to plan and all deployments are nominal, the first images and scientific results from the James Webb Space Telescope can be expected to be delivered about 6 months after launch, in May or June of 2022. Lead image: James Webb Space Telescope undergoes sunshield testing at a Northrop Grumman facility via Northrop Grumman,